Hey everyone, today's video is about the Earth's atmosphere. I noticed that it seems to cause a lot of confusion in flat earthers' brains, so let's start from the beginning. What is an atmosphere and how do planets get them? A planet has an atmosphere when vapors rise from its interior, when it absorbs volatile substances from crashed comets and asteroids, or when it attracts gas from the interplanetary space and holds them due to gravity. But an atmosphere can disappear again, sometimes in a single cosmic moment, sometimes over a long period of time. On Earth, for example, the current loss rate of the two lightest gases is low. For hydrogen it's only about 3 kilograms per second, for helium it is 50 grams. Sounds a lot, right? Well, the mass of the atmosphere is about 5 quadrillion tons. It weighs on the Earth's surface with a mean pressure of about 1000 millibars. This air pressure makes it possible for water to exist in liquid form on the solid Earth's surface. But let's focus on the atmosphere itself. The atmosphere has a higher density at the bottom than at the top. The higher you rise in the atmosphere, the less atmosphere is above you and the lower is the pressure. At 6 kilometers altitude, you have 30% of the atmosphere below you. At 40 kilometers altitude, it's already 99%. The atmosphere contains different layers with different properties. The first one is the troposphere, which reaches from the surface of the Earth up to the tropopause at heights between 7 kilometers in polar regions and 17 kilometers in the tropics. In the troposphere, warmer air is beneath cooler air. This condition is unstable. The warm air near the surface rises and cool air higher in the troposphere sinks. So air in the troposphere does a lot of mixing. This mixing causes the temperature gradient to vary with time and place. The rising and sinking of air in the troposphere causes all of the planet's weather. This lower layer of the atmosphere is therefore also called the weather layer. Also in the troposphere, the scattering of sunlight at the air molecules makes the sky look blue. The temperature in the troposphere decreases with increasing altitude down to -50 to -60 degrees Celsius. It is bounded by the tropopause. Above the tropopause follows the stratosphere that reaches up to the stratopause in about 50 kilometers high. In the stratosphere, temperature increases with altitude because the infamous ozone layer is located in the upper layer. Ozone molecules absorb the UV light of the sun and convert it into heat. The air in the stratosphere is stable because warmer, less dense air sits over cooler, dense air. As a result, there is little mixing in the air within the layer. Above the stratopause follows the mesosphere up to the mesopause in 80 kilometers altitude. Temperatures in the mesosphere decrease with altitude because there are only few gas molecules to absorb the sun's radiation. The mesosphere is extremely cold, especially at its top, about -90 degrees Celsius. By the way, the mesosphere is the region of the atmosphere where meteors lights up. Then there is the thermosphere up to about 700 kilometers. The density of molecules is so low in the thermosphere that the air molecules can fly several meters until they collide with another air molecule. Therefore, the high energy radiation from the sun reaches the air molecules in the thermosphere unfiltered. This radiation heats up the atoms and the molecules in the outer area of the thermosphere at an altitude of approximately 600 kilometers up to 1700 degrees Celsius and causes the atmosphere particles in this layer to become electrically charged in the ionosphere, which extends from about 80 to 580 kilometers above the planet's surface, but it's that part that contains large amounts of ions and free electrons and, for example, causes the aurora at the poles. An aurora is caused by the impact of accelerated charged particles from the Earth's magnetosphere. The Earth's magnetic field conducts the particles down to the magnetic poles and concentrates them on the oval band around them, where they stimulate the gas atoms to glow with their enormous energy. Both the position of the ovals and the shape of the aurora depends on the intensity of the solar activity. Near-Earth satellites and the International Space Station are orbiting the Earth within the thermosphere. Although the air in the thermosphere is so thin, the air resistance is noticeable in the long term. The height of the ISS decreases by 50 to 150 meters per day due to friction with the molecules. So the onboard computer must compensate for this loss of weight by occasional engine ignition for acceleration in the direction of light. Otherwise, the ISS would inevitably crash. But let's get back to topic. Now we come to the last layer of the atmosphere, and that's the exosphere, which marks the final transition into interplanetary space. But as defined by NASA, is already part of it. There is no real outer limit for the exosphere. The gas molecules finally become so scarce that at some point there aren't any. The exosphere is the only atmosphere layer from which the gas molecules I mentioned earlier can leave the Earth's gravitational field due to their own speed, since there are that few particles that their braking effect can be ignored. It's not that there is just a gradient from atmosphere to space. A little bit of our atmosphere flies constantly off into space. I don't know what on that is so so hard to believe for flat earthers. It's pretty funny that it's easier for them to believe they live on a space pizza snow globe Earth that some god placed there out of nothing than scientific facts, even if there's no evidence at all that this god even exists. But whatever, everyone can believe whatever he wants. But don't try to present your belief as fact if you have no evidence to support it. Flat earthers try that for years and fail all the time. And that's the end of today's video. Thanks for watching, bye bye and stay tuned.